Let's begin an example. And in this example, I'm really going to focus on how we set up the scaffolding for inductive proofs. And then, once we've set up all the scaffolding, we'll go on to complete the proof itself. The theorem that I'm going to prove is the following. For all n greater than or equal to 1, it's the case that the sum from I equals 0 up until n of just the number I itself is equal to a formula in terms of n times n plus 1 divided by 2. So to illustrate an example of what this theorem is saying, so just a quick example here, I am going to assume that n is equal to 4 here, and what the theorem says is that if I consider the sum from I equals 0 up to 4, that's the value of n that I'm plugging in, of the number I itself, well, that's equal by definition to 0 plus 1 plus 2 plus 3 plus 4. And if I check that has value 10. You know what else has value 10? Let's consider the formula here, n times n plus 1 over 2. If I consider that formula and I plug in 4 as the value of n, I need to consider 4 times 4 plus 1 over 2, which is equal to 4 times 5 over 2, which is 20 over 2, which is also equal to 10. So what my theorem says is that this is always true. If I add up the first n integers, I will always get a number that agrees with the formula that I would get by saying, oh, I'm going to look at n times n plus 1 and divide the result by 2. So how would we prove this using induction? Whenever I have an inductive proof, I know every time I have to have a base case and I have to have an inductive step. So what I want to do to start us off with the scaffolding, I want to simply write out what is to be proven in the base case. The hardest part of induction is understanding what is to be proven in each case. So what I first have to do is figure out what value of n should I be looking at for my base case. Well, I see here for all n greater than or equal to 1, and this is usually a pretty reliable hint, the smallest value of n for which my theorem is supposed to work is n equals 1, and so my base case here is going to be n is equal to 1. Next, for my scaffolding, I want to figure out what I need to prove. So I know that n equals 1, and that means we need to show that p of 1 is the current value of n, is true. This means that, what I want to do now is I want to flesh out what p of 1 means. And so I'm going to look at the theorem that I'm claiming to be true, because this formula, this equation, is my p of n. That's what I'm showing to be true in the base case for n equals 1. So what I need to do here is when I consider p of 1, I need to plug in 1 every time I see n, and that means I'm going to consider the sum from I equals 0 to n equals 1 of the sequence I, which is equal, so my theorem claims, to 1 times 1 plus 1 over 2. Now, from here, I could go on to actually prove this fact. I could prove this fact, that the two sides of this equation are equal. I'm not going to do that right now because I'm just focusing on setting up the scaffolding of the base case and the inductive step. So for my base case, I'm just focusing on knowing what the base case is, and then writing out, we need to show that P of 1 is true, and then fleshing that out, cashing it out. This means that I need to prove some kind of mathematical result. So in my base case, I would go on to check this. My inductive step is a little more challenging. So in my inductive step, what do I need to do? I need to let k, I need to pick a k, be greater than or equal to 1, because 1 was my base case. We need to show in the inductive step that P of k implies P of k plus 1. That's the statement that we need to prove. And we often do this, not always, but often, with direct proof. So in this case, my scaffolding continues. How am I going to show this? I'm going to say, hey, therefore, assume that P of k is true. This means, so now that I've made my assumption, I'm doing my direct proof kind of approach. I'm making my assumption that P of k is true. And what I need to do now is I need to apply my definitions. And in this case, my definition of my predicate P of n. So I need to plug in k every time I see n, and therefore this means that the sum from I equals 0 up until k of the sequence I equals k times k plus 1 over 2. So I have said what my base case is, what I'm aiming to prove, and then I've started my direct proof by making an assumption and cashing out that assumption in terms of its definition. Now, what I could do is I could keep going here, but I don't know where I'm going yet. And in order to know where I'm going, I want to look ahead to the end. At the very end, because I'm doing direct proof, P of k implies P of k plus 1, what I want to do is say, therefore, P of k plus 1. That's where I want to get to. In the standard direct proof, if I assume P of k, and then from that assumption, I get to P of k plus 1, I have shown that P of k implies P of k plus 1. So I need to get there. So my last line has to be this, and I can already tell what the line before that is as well, because what's the meaning of P of k plus 1? It's the same statement I keep coming back to, but now I plug in k of k plus 1 every time I see n. So what I want to have proven in the middle of this proof is that the sum from I equals 0 to k plus 1 of the sequence I is equal to, and now I need to be a little bit careful. I'm going to plug in k plus 1 every time I see n, and that means n plus 1 is going to become k plus 2 divided by 2. So this is what I want to show. And then there's going to be something in between that gets me there. So in order to prove this theorem, this relationship between a sum and a formula, what I need to do is I need to set up a base case, and I need to set up an inductive step. And before I start doing any algebra, I just want to make sure I'm really solid on my definitions. What do I need to show? Well, I need to show P of 1 in the base case. What does this mean? This means that the following equation has to be true. Now I know what I'm going to try to prove in the base case. What am I trying to show in the inductive step? I'm going to pick a k. I need to show that P of k implies P of k plus 1. That's what I do in every induction. Therefore, assume that P of k is true. What does this mean in terms of definitions? It means that this equation is true. And now, skip ahead, where am I going? I want to show that P of k plus 1 is true, and that means I have a definition of that as well. Now I know what my task is. I need to use math and algebra to get from this equation to that equation. And so how do I get from this equation to that equation is our next topic. Okay, so we've created some scaffolding. We have some scaffolding of our theorem that the sum of all the natural numbers up to n agrees with this formula, n times n plus 1 divided by 2. So in order to construct the scaffolding, to lay out our plan for our proof by induction, we have a base case, we have an inductive step, and we know what we need to prove in each one. So in the base case, n equals 1, we need to show that p of 1 is true. And this means that the sum of all the natural numbers from I equals 1 up to 0, up to 1, is equal to 1 times 1 plus 1 over 2. So that's what we want to show. So now let's go ahead and actually do the showing. How do we prove that? I'm going to erase these dots here. So how do we actually prove this? This one is pretty easy, and that's because the sum, we have that the sum from I equals 0 to 1 of I itself, that's just 0 plus 1, which is equal to 1. Also, if we check, 1 times 1 plus 1 is over 2 is equal to 1 times 2 divided by 2, which is 1. And really here I'm done. These two statements agree. I am happy. I have shown that the base case is true. When I plug in I equals 1, this equation is correct. For my inductive step, things can be a little bit more complicated. So remember that my scaffolding is as follows. I choose any k greater than or equal to my base case, in this case 1. And I need to show that p of k being true implies that p of k plus 1 is true. Therefore, I assume that p of k is true, and this means that I'm living in a world in which I know, or at least I'm imagining that I know, that this equation is correct about k. I don't know it for any other values, but I know that when I plug in k into this equation, it's going to work. So how can I use that in order to get where I want to go, which is that when I plug in k plus 1, I'm going to get the right answer. How can I use that to show that I'm going to get there? So I'm going to erase these dots as well. Okay, so what I'm going to do is I'm going to do a direct calculation with some algebra involved. So here's what we do. I'm going to evaluate the sum from I equals 0 to k plus 1 of I. So this is the left-hand side of where I want to go, and I'm going to do some algebra to show that I can get to the right-hand side as well. So this sum is equal to, well, if I add up all the integers up to k plus 1, I could instead add up all the integers up to k and then add k plus 1. That's the same thing. I'm just taking the k plus 1 part out. What's left is all the natural numbers up to k. Okay, but here's something. I know something about this sum because that's the sum that appears in my assumption. Thus, in the world of my assumption, I've assumed that the sum from I equals 0 up to k of I is equal to k times k plus 1 over 2. Because I'm in this world, I can replace this sum with that formula, k times k plus 1 divided by 2, plus k plus 1. So I'm making this replacement from here to here, and this is because I assumed that p of k is true. Sometimes p of k is called my inductive hypothesis. It's the thing that I assume to be true in order to facilitate my inductive proof. Okay, so now I'm making really good progress because I just need to make sure that I can show that this formula is the same as this formula. And that's just some algebraic simplification now. I've actually already done the hard part. So what I'm going to do is I'm going to say, okay, that's equal to k times k plus 1 over 2. I'm not touching the first term at all. And then on the second term, I'm going to multiply it by 2 divided by 2. So that's 2 times k plus 1 divided by 2. Now I have a shared denominator, and I also see how many copies of k plus 1 do I have. I have k copies here and 2 copies here, all divided by 2, which means that I can simplify further. I have k plus 2 copies of k plus 1, all divided by 2. And that's what I wanted to prove. I wanted to get here, and here I am. So once I've set up my scaffolding correctly, especially in my inductive step, I know that I want to show an implication. I assume the first part of the implication, the antecedent. I cache it out in terms of my definitions. And I chart my course. I say, okay, I want to prove that p of k plus 1. This would have meant that in terms of my definitions, that something is true. Once I can do those things, actually getting from the beginning to the end is often just a matter of starting with something you know is relevant to the end, like the sum up to k plus 1, and then being a little clever about where you use your inductive hypothesis, where you assume that p of k is true. In this case, what I had to do is I had to turn this sum involving k plus 1, I had to break it up into a part involving k, which I knew about because it was related to my inductive hypothesis, plus some other stuff. Then I applied my inductive hypothesis, and then I had to combine the result with the other stuff, and eventually I got to where I wanted to go. So inductive proofs don't have to be extremely complicated if we take the time to carefully set up what's our base case and what are our definitions that we need to show. And then in our inductive step, pick a k, we need to show an implication, therefore assume the first part, cache it out in terms of the definition, and so on. We'll do many more examples of inductive proofs soon.